You walk outside to water your garden, thinking you're helping your plants survive. Instead, you're about to trigger a cascade of cellular destruction that transforms healthy soil into a suffocating environment. Research reveals that watering at certain times creates hypoxic conditions in your soil, where oxygen diffusion rates drop by 10,000 times compared to well-drained conditions. Your plant roots, suddenly starved of oxygen, begin producing toxic metabolites like ethanol that poison the very system you're trying to save. The timing of when you turn on that hose determines whether your plants access life-giving moisture or face systematic cellular breakdown. 3 specific watering windows create these deadly conditions. The first deadly window strikes after sunset, when most gardeners reach for the hose, convinced that cooler nighttime temperatures prevent water loss through evaporation, while allowing maximum moisture to penetrate the root zone. This logic appears sound on the surface. Reduced heat stress means less water demand from the plant, and the absence of blazing sunlight eliminates the rapid moisture loss that occurs during daytime irrigation. But when you water your garden after dark, you activate a biological weapon system that lies dormant throughout daylight hours. Fungal spores that remain inactive under UV radiation suddenly spring to life in the cool, moist environment created by wet foliage. These microscopic organisms have evolved sophisticated survival mechanisms that allow them to detect the precise combination of moisture, temperature, and darkness that signals optimal conditions for colonization. The process begins within minutes of water contact with leaf surfaces. Fungal spores, carried by wind currents and previously deposited on plant tissues, absorb moisture and begin germination. The absence of UV radiation removes the primary natural sterilization mechanism that keeps these pathogens in check during daylight hours. Without this solar disinfection, spore populations multiply exponentially in the protective darkness. Common garden diseases like powdery mildew and black spot thrive when leaf surfaces remain wet during extended periods of cool, dark conditions. These pathogens establish viable colonies through a systematic invasion process that wet leaves in darkness make inevitable. The fungi produce specialized compounds that break down the protective barriers on leaf surfaces, creating direct pathways into vulnerable plant tissues. The invasion occurs through natural openings called stomata, tiny pores that regulate gas exchange between the plant and atmosphere. During nighttime hours, these stomata remain open longer than during daylight to facilitate carbon dioxide uptake and oxygen release. This extended opening period provides disease organisms with direct access to the plant's internal cellular structure, bypassing the primary defense barriers that would otherwise protect against infection. Once inside, the systematic destruction begins as these organisms consume nutrients and disrupt normal metabolic processes. The cellular damage spreads rapidly throughout the plant's vascular system, compromising structural integrity and overwhelming the plant's ability to maintain healthy function. The cool temperatures that make nighttime watering seem advantageous actually accelerate pathogen development. Most plant diseases thrive in temperatures between 60 and 75 degrees Fahrenheit, ranges commonly experienced during evening and early morning hours. These conditions optimize biological activity within disease organisms, allowing rapid reproduction and tissue colonization. Without morning sunlight to activate natural plant defense compounds, infected tissues cannot mount effective resistance against the spreading pathogens. Plants normally produce antimicrobial substances like phenolic compounds and pathogenesis-related proteins when exposed to solar radiation. Nighttime watering circumvents this crucial defense activation, leaving plants vulnerable throughout the critical infection period. The moisture retention created by nighttime irrigation extends far beyond normal dew formation. While natural dew typically evaporates within hours of sunrise, artificially applied water can persist on leaf surfaces for 8 to 10 hours when applied after sunset. This prolonged wetness period provides ample time for complete disease establishment and secondary reproduction cycles. Professional agricultural operations avoid this pathogen proliferation by scheduling irrigation during early morning hours when rapid surface drying occurs. Commercial greenhouse operations typically begin watering before dawn, ensuring that all plant surfaces dry completely within 2 to 3 hours of sunrise. This timing provides adequate soil moisture while minimizing the leaf wetness duration that promotes disease development. The cellular destruction triggered by nighttime watering creates cascading failures throughout plant systems. Toxins produced during colonization disrupt photosynthetic processes, reducing the plant's ability to generate energy from sunlight. Simultaneously, damaged leaf tissues lose their ability to regulate water loss, creating additional stress that compounds the original pathogen damage. Root systems suffer secondary impacts as plants redirect energy resources toward fighting foliar infections. This metabolic shift reduces root growth and nutrient uptake capacity, weakening overall plant vigor and creating susceptibility to additional stressors like drought or nutrient deficiency. The combined effects can kill otherwise healthy plants within days of initial infection. Temperature fluctuations during overnight periods create additional complications for disease-prone plants. Rapid cooling after sunset can cause water droplets to condense on leaf surfaces, even without irrigation, extending the moisture exposure period. When combined with applied water, this natural condensation creates ideal conditions for explosive pathogen growth. The biological warfare that emerges from nighttime watering operates with systematic precision. Disease organisms coordinate their establishment through chemical signaling systems that optimize colony placement and resource utilization. This destruction unfolds silently while gardeners sleep, unaware that their well-intentioned care has triggered plant devastation. By morning, the damage has begun, and the infection cycle continues with each subsequent watering event that maintains the deadly pattern of prolonged darkness and moisture exposure. Yet darkness represents only one of the 3 lethal watering windows. When blazing heat arrives and your plants begin drooping under intense solar radiation, the instinct to provide immediate relief creates an entirely different form of cellular destruction. This thermal destruction unfolds through a process that contradicts every logical assumption about plant care during extreme heat. When the thermometer climbs above 85 degrees Fahrenheit and you witness your plants drooping under the relentless solar assault, every instinct demands immediate intervention. The wilting leaves and stressed appearance trigger an urgent response. Grab the hose and deliver cooling relief to the suffering vegetation. This rescue mission seems perfectly logical. Plants clearly need water to survive extreme heat, and immediate action prevents permanent damage from occurring. The moment cold water contacts superheated soil surfaces, you initiate a thermal shock sequence that surpasses drought stress in its destructive potential. Extreme temperature differentials between irrigation water and heated soil create rapid thermal expansion and contraction cycles within the soil matrix. When irrigation water at 60 to 70 degrees Fahrenheit suddenly contacts these superheated surfaces, the temperature differential creates mechanical stress that targets the most vulnerable components of the root system. These extreme temperature fluctuations damage the microscopic root hairs responsible for water and nutrient absorption. Root hairs operate as delicate cellular extensions that maximize surface area contact with surrounding soil particles. Their thin walls and extended structure make them extraordinarily sensitive to sudden environmental changes, particularly temperature variations that exceed normal thermal gradients. The cellular damage occurs within seconds of water contact, as rapid contraction, followed by yet immediate expansion, causes membrane rupture and eliminates the primary absorption interface between plant and soil. During peak heat periods, plants activate sophisticated survival mechanisms designed to minimize water loss through transpiration. Stomatal pores, the microscopic openings on leaf surfaces that regulate gas exchange, close automatically when temperatures exceed optimal ranges. This closure prevents excessive moisture loss, but simultaneously blocks the plant's ability to process incoming water from irrigation systems. The plant essentially shuts down its primary water processing mechanism just when artificial irrigation attempts to flood the system with moisture. The closed stomatal condition creates a physiological bottleneck where water enters through the root system but cannot exit efficiently through normal transpiration pathways. This imbalance overwhelms the plant's internal water regulation systems, causing cellular pressure to build within leaf tissue. The excessive internal pressure can rupture cell walls and disrupt normal metabolic processes, creating damage that extends beyond simple heat stress. The fundamental inefficiency of midday irrigation becomes apparent when examining how heat-stressed plants process water. Heat-stressed plants demonstrate significantly reduced water absorption rates during midday hours compared to cooler periods. The physiological processes that drive water uptake slow dramatically when temperatures exceed optimal ranges, making irrigation during these periods largely ineffective for addressing plant water needs. The energy normally allocated to water absorption gets redirected toward heat stress responses, creating a metabolic shift that actually reduces the plant's ability to utilize available moisture. Most water applied during peak heat periods evaporates rapidly from soil surfaces before reaching root zones, wasting the resource while failing to address the plant's actual hydration needs. The combination of reduced absorption capacity and rapid evaporation means that midday watering delivers minimal benefit while subjecting plants to thermal shock stress. The plant's transpiration system, designed to operate within specific temperature and moisture ranges, becomes completely overwhelmed when forced to process sudden water influxes during peak heat conditions. Transpiration normally functions as a regulated cooling mechanism where water movement through plant tissues removes excess heat while delivering nutrients from soil to leaves. When this system receives massive water inputs while stomata remain closed, the normal flow patterns become disrupted, leading to cellular breakdown as water accumulates faster than the plant can regulate its distribution. Professional agricultural operations recognize these physiological limitations and schedule irrigation during dawn hours when soil temperatures remain stable and plant systems can efficiently process incoming water. Commercial greenhouse facilities typically begin watering cycles before sunrise, ensuring that soil moisture reaches optimal levels while avoiding the thermal stress associated with midday irrigation. This timing allows plants to hydrate their tissues during cool morning hours when stomata open naturally and transpiration systems function at peak efficiency. The temperature stability provided by early morning irrigation creates optimal conditions for water absorption without subjecting root systems to damaging thermal fluctuations. Soil temperatures during pre-dawn hours typically remain within moderate ranges of air temperature, eliminating the extreme differentials that cause cellular damage during peak heat periods. Industrial farming operations demonstrate that proper irrigation timing can mean the difference between thriving crops and systematic plant destruction, even when identical water volumes are applied under different thermal conditions. Morning watering allows plants to build adequate tissue hydration before facing daily heat stress, creating resilience that midday rescue attempts cannot provide. This preparation proves far more effective than attempting emergency intervention when plants already show stress symptoms. Yet, even perfect timing cannot overcome the most insidious threat to plant survival, one that operates silently beneath the soil surface, where excess water transforms healthy growing medium into something far more dangerous. Beneath this deceptively normal surface lies a suffocating environment where oxygen concentrations have plummeted to levels that would kill human beings within minutes. The microscopic air pockets that normally honeycomb healthy soil have filled completely with water, creating an underground chamber where oxygen diffusion rates drop by 10,000 times compared to well-drained conditions. This dramatic reduction in oxygen availability occurs because water molecules are significantly larger and more tightly packed than air molecules. When excessive irrigation fills every available pore space, the normal pathways for atmospheric oxygen to reach root systems become completely blocked. The soil transforms from a living, breathing ecosystem into an aquatic environment that lacks the dissolved oxygen levels necessary to support terrestrial plant life. Root cells, suddenly deprived of their primary energy source, face an immediate biological crisis that threatens their survival within hours. Normal cellular respiration requires a constant supply of oxygen to power all cellular functions. Without oxygen, these energy-producing processes halt completely, forcing root systems into emergency survival mode. The desperate cells switch to anaerobic metabolism, a primitive energy production system that generates only a fraction of the power produced by normal respiration. This emergency process creates toxic byproducts, including ethanol, aldehydes, and lactic acid that accumulate rapidly within cellular structures. These metabolic waste products poison the very cells that produce them, creating a cascading failure that spreads throughout the root system. The rhizosphere, normally a thriving community of beneficial microorganisms that support plant health, undergoes complete ecological collapse under waterlogged conditions. Aerobic bacteria that normally decompose organic matter and cycle nutrients suffocate and die within hours of oxygen depletion. Their place gets taken by anaerobic bacteria that produce hydrogen sulfide, methane, and other toxic compounds that further damage root tissues. Plants respond to this underground catastrophe by flooding their systems with stress hormones, particularly ethylene production, that increases by hundreds of times normal levels. This hormone surge triggers premature leaf yellowing and drop as the plant attempts to reduce its energy demand and survive the root system crisis. The ethylene also accelerates root decay processes, creating a destructive feedback loop that compounds the original oxygen starvation. The energy crisis created by oxygen depletion cripples the plant's ability to absorb nutrients from surrounding soil, even when fertilizers are present in abundance. Without adequate energy production, the transport mechanisms that normally move minerals from soil into root cells shut down completely, leaving plants unable to access available nutrition. Water absorption itself becomes compromised as root cell membranes lose their structural integrity under anaerobic conditions. The cellular systems that regulate water uptake require oxygen-dependent energy to maintain proper function. As these systems fail, roots begin to leak cellular contents into surrounding soil, further damaging the underground ecosystem. The dying root tissues release enzymes and cellular components that create ideal conditions for pathogenic organisms to establish colonies. Fungal pathogens that normally cannot penetrate healthy root barriers exploit the weakened cellular defenses to invade plant tissues. These secondary infections accelerate the destruction process and often prove more lethal than the original oxygen starvation. Cell death spreads systematically upward through the plant's vascular system as damaged roots fail to supply water and nutrients to above-ground portions. The transportation network that normally carries resources from soil to leaves becomes progressively compromised as root function deteriorates. Leaves begin showing symptoms of drought stress even though soil moisture remains excessive, creating the paradoxical situation where plants die of thirst while surrounded by water. The destruction occurs at the molecular level as anaerobic conditions generate massive quantities of reactive oxygen species that attack cellular DNA, proteins, and lipid membranes. These highly destructive molecules overwhelm the plant's natural antioxidant defense systems, causing widespread cellular damage that proves irreversible even if soil conditions improve. Professional agricultural operations prevent this underground suffocation by implementing drainage systems that maintain optimal soil oxygen levels throughout the growing season. Commercial greenhouse facilities monitor soil air content using specialized sensors that detect when oxygen concentrations drop below critical thresholds for plant survival. Proper drainage and soil structure matter more for plant survival than total water volume applied during irrigation cycles. The timing and volume of irrigation applications get carefully calculated to provide adequate moisture without eliminating the air spaces essential for root respiration. Advanced irrigation systems deliver water in measured doses that saturate the root zone without creating the waterlogged conditions that trigger oxygen starvation. Recovery from severe waterlogging requires plants to remobilize nutrients and rebuild damaged root systems while combating oxidative stress from accumulated toxins. Even plants that survive the initial oxygen crisis face months of reduced growth and increased susceptibility to additional stressors as they repair the cellular damage caused by anaerobic metabolism. The biochemical chaos unleashed by oxygen starvation reveals only the beginning of waterlogged soil's destructive power. When normal cellular respiration becomes impossible, root cells must find alternative pathways to generate the energy needed for survival. These alternative pathways transform root cells into microscopic fermentation facilities that operate with the same biochemical processes found in commercial breweries. The cellular machinery designed for efficient aerobic respiration shuts down completely, forcing desperate root tissues to activate primitive anaerobic pathways that generate energy through fermentation processes. These emergency metabolic systems produce ethanol as a primary byproduct, along with aldehydes, lactic acid, and other toxic compounds that accumulate rapidly within the confined cellular environment. The fermentation process begins within hours of oxygen depletion as root cells attempt to maintain basic metabolic functions through glycolysis and ethanol fermentation pathways. These anaerobic systems generate adenosine triphosphate at drastically reduced efficiency levels compared to normal aerobic respiration. creating an immediate energy crisis that compromises essential cellular operations. The biochemical machinery operates under extreme stress conditions, producing toxic metabolites at rates that quickly overwhelm the plant's natural detoxification capacity. Ethanol concentrations within waterlogged root tissues can reach levels that would prove lethal to human cells, creating an internal poisoning scenario that spreads throughout the root system. The alcohol accumulates faster than cellular mechanisms can process or eliminate it, building to concentrations that disrupt normal membrane function and cellular integrity. Root cell membranes, exposed to these toxic alcohol levels, begin to lose their selective permeability and structural stability, allowing cellular contents to leak into surrounding tissues. The enzyme alcohol dehydrogenase activates as the plant's primary defense mechanism against rising ethanol concentrations, working to convert the toxic alcohol into less harmful compounds. This crucial enzyme experiences dramatic upregulation as plant systems detect the presence of dangerous alcohol levels within root tissues. However, the enzyme systems quickly become overwhelmed as ethanol production rates exceed the cellular capacity for detoxification, creating a biochemical bottleneck that allows toxin accumulation to continue unchecked. Simultaneously, the stressed cellular environment generates massive quantities of reactive oxygen species that flood root tissues with highly destructive molecular compounds. These aggressive molecules attack cellular DNA, destroying genetic material and disrupting normal protein synthesis processes. The oxidative assault extends to lipid membranes that maintain cellular structure, causing widespread damage that compromises the fundamental architecture of root cells. The plant's natural antioxidant systems, evolved to handle normal metabolic waste products, cannot cope with the massive influx of toxic compounds generated by anaerobic fermentation. Cellular detoxification mechanisms, designed to process small quantities of metabolic byproducts, become completely saturated when forced to handle the industrial-scale toxin production created by waterlogged conditions. Root tips suffer the most severe damage because their high metabolic activity generates proportionally larger quantities of toxic fermentation byproduct. These actively growing regions consume energy at accelerated rates, forcing them to rely heavily on anaerobic metabolism when oxygen becomes unavailable. The combination of high toxin production and concentrated metabolic activity creates lethal conditions that kill root tip tissues within hours of oxygen depletion. The cellular destruction spreads systematically from root tips toward the main stem as toxic metabolites circulate through the plant's vascular system. Progressive tissue death follows predictable pathways as ethanol and other fermentation byproducts travel through transportation networks designed to carry nutrients and water to above-ground plant portions. The expanding zone of cellular death creates cascading failures that ultimately compromise the entire root system's ability to support plant survival. Additional toxic compounds produced during anaerobic metabolism create multiple pathways of cellular damage that compound the ethanol poisoning effects. These reactive compounds bind to cellular proteins and disrupt normal enzymatic functions, interfering with DNA replication and protein synthesis. The accumulated toxicity contributes to permanent cellular damage that makes recovery from severe waterlogging extremely difficult for affected plants. Commercial agricultural operations recognize these biochemical dangers and implement precise irrigation scheduling that prevents soil oxygen depletion. Professional greenhouse facilities monitor soil air content to ensure that root systems never experience the anaerobic conditions that trigger toxic fermentation processes. These operations maintain optimal soil moisture levels without creating the waterlogged conditions that transform healthy root systems into toxic fermentation facilities. Even brief periods of soil saturation can cause permanent damage in sensitive plant species because the biochemical destruction begins immediately when oxygen levels drop below critical thresholds. The cellular damage accumulates rapidly, making prevention through proper irrigation timing far more effective than attempting to remediate the toxic effects after they occur. Understanding these fermentation processes reveals why waterlogged soil creates conditions more destructive than temporary drought stress for most garden plants. The systematic poisoning unleashed by anaerobic fermentation demonstrates the critical importance of maintaining soil oxygen levels through proper watering practices. Yet when irrigation timing aligns with natural biological cycles, water transforms from a destructive force into a catalyst that activates sophisticated protective mechanisms within plant tissues. The first rays of sunlight trigger a biological awakening within plant tissues that transforms ordinary garden specimens into biochemical powerhouses capable of neutralizing environmental threats before damage occurs. This dawn activation sequence operates with precision timing that synchronizes water availability with peak antioxidant enzyme production, creating optimal conditions for cellular protection throughout the demanding daylight hours ahead. Most gardeners apply water based on convenience or visual plant appearance, completely unaware that irrigation timing determines whether their plants develop robust defense systems or remain vulnerable to oxidative destruction. Morning light combined with adequate soil moisture activates a sophisticated network of protective enzymes that function as molecular guardians against cellular damage. The timing of this activation process depends entirely on the synchronization between photosynthetic light reactions and water availability within plant tissues. When these two critical factors align during dawn hours, plants initiate cascading biochemical processes that generate massive quantities of protective compounds designed to neutralize harmful reactive oxygen species before they can attack cellular structures. Peroxidase enzymes reach peak activity levels within hours of sunrise, when soil moisture provides optimal hydration for enzyme synthesis and activation. These specialized proteins catalyze reactions that convert dangerous hydrogen peroxide into harmless water and oxygen molecules, preventing oxidative damage to essential cellular components. The peroxidase system operates most efficiently when plants receive adequate water during the early morning hours, allowing enzyme concentrations to build throughout the pre-dawn period before environmental stresses intensify. Catalase enzymes work in coordination with peroxidase systems to decompose hydrogen peroxide that accumulates during normal cellular metabolism and stress responses. These enzymes demonstrate remarkable activity increases when morning watering provides the hydration necessary for optimal function. The catalase system requires adequate cellular water content to maintain structural integrity and catalytic efficiency throughout periods of intense photosynthetic activity and environmental stress. Superoxide dismutase enzymes target the most reactive oxygen species produced during photosynthesis and stress metabolism, converting dangerous superoxide radicals into less harmful hydrogen peroxide that other enzyme systems can neutralize. These critical enzymes achieve maximum activity levels when morning irrigation ensures adequate cellular hydration for proper enzyme assembly and function. The superoxide dismutase system represents the first line of defense against oxidative damage, making its optimal function essential for plant survival under stress conditions. These molecular guardians operate through coordinated biochemical pathways that neutralize harmful reactive oxygen species before they can damage cellular DNA, proteins, and lipid membranes. The enzyme systems work in sequential order, with superoxide dismutase converting the most dangerous radicals into intermediate compounds that catalase and peroxidase can process into harmless byproducts. This coordinated approach ensures comprehensive protection against oxidative damage when adequate water supplies support optimal enzyme function. Morning watering allows plants to fully hydrate their antioxidant systems during the critical preparation period before facing intense UV radiation and heat stress later in the day. The early morning hours provide optimal conditions for water uptake and distribution throughout plant tissues, ensuring that protective enzyme systems receive adequate hydration for maximum effectiveness. This preparation phase proves crucial because antioxidant enzymes require significant water content to maintain their protective functions during periods of environmental stress. The plant's natural circadian rhythms synchronize water uptake with peak photosynthetic activity, creating optimal timing for energy production and defense compound synthesis. Internal biological clocks regulate stomatal opening patterns, root absorption rates, and enzyme production schedules to maximize resource utilization during dawn hours. When irrigation timing aligns with these natural rhythms, plants achieve maximum efficiency in converting water and light energy into protective compounds that ensure survival throughout challenging daylight conditions. Ascorbate molecules reach optimal concentrations when water delivery coordinates with the plant's biological clock, providing powerful antioxidant protection that supplements enzyme-based defense systems. These vitamin C compounds function as mobile antioxidants that can neutralize reactive oxygen species throughout plant tissues, offering protection in cellular locations where large enzyme molecules cannot operate effectively. Glutathione production increases dramatically when morning irrigation provides the hydration necessary for amino acid metabolism and protein synthesis pathways. This tripeptide antioxidant functions as both a direct reactive oxygen species scavenger and a cofactor for numerous protective enzyme systems. Glutathione concentrations directly correlate with water availability during morning hours, making irrigation timing critical for optimal antioxidant protection. The synchronization between water availability and circadian-controlled antioxidant production creates a biological amplification effect, where proper irrigation timing multiplies the plant's natural protective capacity. Plants that receive water during optimal circadian windows demonstrate significantly higher antioxidant enzyme activities and protective compound concentrations compared to those watered at random times. Morning watering activates comprehensive antioxidant defense systems by working with the plant's natural biological clock rather than against it. The coordinated activation of peroxidase, catalase, superoxide dismutase, ascorbate, and glutathione systems creates overlapping protection layers that neutralize oxidative threats before cellular damage occurs. This biochemical preparation ensures that protective compounds reach maximum concentrations before daily environmental stresses challenge plant health. Yet even perfect timing cannot overcome fundamental flaws in how most gardeners measure water application. The widely accepted guidelines that govern irrigation schedules ignore the invisible forces that actually determine whether water reaches plant roots. Soil moisture tension reveals the invisible physics that determines whether plants can actually extract water from surrounding soil particles, regardless of total volume present. This measurement quantifies the energy that roots must expend to pull water molecules away from soil surfaces, providing accurate information about true water availability rather than simple volume calculations. The tension measurement operates like a molecular tug-of-war between plant roots and soil particles, where victory determines whether plants thrive or experience water stress despite abundant soil moisture. The widely accepted 1 inch per week watering rule treats every garden as identical, ignoring these fundamental physics of how water molecules bind to soil particles. This arbitrary measurement system fails to account for soil composition, plant species requirements, and environmental conditions that dramatically affect water availability. Gardens operating under this simplistic volume-based approach experience systematic overwatering in clay soils and chronic underwatering in sandy conditions, creating the exact problems that proper irrigation should prevent. Clay soils demonstrate the critical importance of tension measurements by holding water so tightly that plants cannot extract it even when soil appears saturated with moisture. The microscopic clay particles create powerful binding forces that hold water molecules with energy exceeding the extraction capacity of most plant root systems. These soils can contain massive water volumes while simultaneously creating drought conditions for plants attempting to access the tightly bound moisture through normal physiological processes. Sandy soils present the opposite challenge by allowing water to drain so rapidly that root systems cannot absorb adequate moisture before gravitational forces pull it beyond the reach of shallow root zones. The large particle size and minimal binding forces in sandy soils create excellent drainage conditions that eliminate water availability windows necessary for sustained plant hydration. Plants growing in sandy conditions require frequent irrigation applications timed to coincide with periods when water remains within the active root zone. Optimal plant water extraction typically occurs when soil moisture tension falls within moderate ranges, where water molecules remain accessible to root absorption mechanisms without requiring excessive energy expenditure. Below these ranges, soil conditions often indicate waterlogged environments that create the oxygen starvation problems discussed in previous sections. Above these ranges, water extraction becomes increasingly difficult as soil particles hold moisture with forces that exceed the capabilities of most plant species. Different plant species demonstrate remarkable variation in their ability to extract water at different tension levels, making universal watering schedules ineffective for mixed gardens containing diverse plant types. Desert-adapted plants possess specialized root structures and biochemical mechanisms that enable water extraction at high tension levels, while tropical species require moisture availability at low tension levels for optimal growth. These evolutionary adaptations explain why some plants thrive under conditions that prove lethal to others, despite identical soil moisture volumes. Professional agricultural systems employ tensiometers to measure this invisible force directly, adjusting irrigation schedules based on actual plant water stress rather than calendar dates or visual plant appearance. These precision instruments detect changes in soil moisture tension that occur hours or days before plants show visible signs of water stress, allowing proactive irrigation management that prevents damage before it occurs. Commercial greenhouse operations rely on tensiometer networks to optimize water application timing and volume across different soil zones and plant species. The simple finger test actually measures soil moisture tension through the physical resistance encountered when pressing into soil profiles at different depths. When soil feels dry and crumbly at finger insertion, tension levels have typically exceeded the optimal range for most garden plants, indicating immediate irrigation needs. Conversely, soil that feels saturated or muddy often indicates tension levels below the critical threshold, suggesting drainage problems or overwatering conditions that require corrective action. Soil composition dramatically affects the relationship between moisture content and tension levels, creating situations where identical water volumes produce vastly different plant-available moisture conditions. Organic matter content, particle size distribution, and soil compaction levels all influence how tightly water binds to soil surfaces and becomes available for root extraction. These factors explain why gardening advice that works perfectly in one location proves completely ineffective in different soil environments. The finger test provides practical soil moisture tension assessment by revealing the force required to penetrate soil layers at various depths throughout the root zone. Resistance levels encountered during finger insertion correlate directly with the energy that plant roots must expend to extract water from the same soil environment. This simple technique allows gardeners to assess actual plant water availability rather than relying on surface moisture conditions that can mislead irrigation decisions. Understanding soil moisture tension creates a feedback system that responds to actual plant water stress rather than following rigid schedules that ignore environmental variables and soil physics. This approach optimizes water use efficiency while preventing both drought stress and waterlogging conditions that trigger the destructive processes outlined in previous sections. When gardeners monitor tension levels through practical assessment methods, they create responsive irrigation systems that adapt to changing conditions rather than imposing arbitrary water volumes regardless of actual plant needs. This monitoring approach transforms your garden into an interconnected biological system where rainfall patterns, plant transpiration rates, and soil composition create continuous feedback loops that regulate moisture availability throughout the growing season. Most gardeners apply water according to rigid weekly schedules that ignore these dynamic environmental interactions, creating systematic overwatering or underwatering conditions that stress plants regardless of actual moisture needs. This mechanistic approach treats gardens like industrial assembly lines rather than living ecosystems where multiple variables interact to determine optimal irrigation timing and volume requirements. Understanding these system-wide interactions requires recognizing how each component influences moisture availability and plant water demands in real-time responses to changing environmental conditions. Rainfall provides the primary water input, but soil particle composition determines how much precipitation becomes available for root absorption versus running off surfaces or draining beyond the reach of shallow root systems. Clay soils retain massive water volumes while sandy soils allow rapid drainage, creating vastly different availability patterns from identical rainfall amounts. Plant species and developmental stages generate varying transpiration demands that fluctuate dramatically throughout growing seasons as root systems expand and leaf surface areas increase. Young seedlings with limited root development require frequent shallow watering to maintain soil moisture within their restricted root zones, while mature plants with extensive root systems can extract water from deeper soil layers and tolerate longer intervals between irrigation applications. These changing demands create dynamic dynamic water requirements that fixed scheduling systems cannot accommodate effectively. Mulch layers function as moisture regulation systems that modify evaporation rates and soil temperature fluctuations throughout daily heating and cooling cycles. Organic mulches absorb initial rainfall amounts before allowing deeper soil penetration, creating temporary water storage that releases moisture gradually during dry periods. The 2 to 3 inch mulch barrier reduces surface evaporation rates by shielding soil from direct solar radiation and wind exposure, extending the availability of applied water while maintaining more stable soil temperatures that reduce plant stress levels. Weather pattern variations create moisture demand equations that extend beyond simple temperature measurements used in most irrigation scheduling systems. Humidity levels determine transpiration rates as plants respond to atmospheric moisture content by adjusting stomatal opening patterns and water loss rates. Wind exposure accelerates moisture loss through both soil surface evaporation and increased plant transpiration, creating higher water demands during breezy conditions even when temperatures remain moderate. The feedback loop emerges when you integrate soil moisture monitoring with direct plant observation techniques that reveal actual stress indicators rather than relying on predetermined watering schedules. This integrated monitoring approach mirrors the precision agriculture principles used in commercial operations, where multiple assessment methods provide comprehensive data about actual plant water status. Professional agricultural systems employ similar monitoring techniques to optimize irrigation efficiency while preventing both drought stress and waterlogging conditions. Rainfall measurement using simple rain gauges provides baseline data for calculating weekly precipitation totals that determine whether supplemental irrigation becomes necessary for optimal plant health. The finger test performed at depths throughout the active root zone reveals soil moisture tension conditions that indicate when plants can extract adequate water versus when irrigation support becomes essential for preventing stress damage. These assessment techniques provide more relevant moisture information than surface observations that can mislead irrigation decisions. Plant observation protocols reveal early stress indicators, including subtle leaf color shift, reduced morning turgidity, and decreased growth rates that signal developing moisture deficits before visible wilting occurs. These biological indicators respond to actual plant water status rather than soil moisture content alone, providing feedback about whether applied water reaches root systems effectively or whether drainage problems prevent adequate uptake despite abundant soil moisture. Targeted water delivery systems, including drip irrigation and soaker hoses, eliminate leaf wetness that promotes fungal disease development while delivering moisture directly to root zones where plants can access it efficiently. These precision application methods prevent water waste through evaporation and surface runoff while maintaining optimal soil moisture conditions without creating the waterlogged environments that trigger anaerobic metabolism and toxic compound production. The integrated system creates continuous feedback between environmental inputs, plant responses, and irrigation applications that optimize water use efficiency while preventing both drought stress and waterlogging damage. This dynamic approach ensures that every irrigation application supports plant health by responding to actual system requirements rather than arbitrary volume targets that ignore the complex interactions governing plant water availability and utilization throughout changing environmental conditions. Commercial agricultural operations demonstrate that sophisticated irrigation management requires surprisingly straightforward measurement techniques that focus on the biological and physical factors that actually determine plant water stress. These assessment methods require specific tools that transform complex irrigation decisions into straightforward measurement protocols accessible to any gardener willing to monitor actual plant conditions rather than following arbitrary schedules. A simple rain gauge positioned in an open area away from structures and vegetation provides accurate precipitation measurements that form the foundation for calculating whether supplemental irrigation becomes necessary during any given week. The gauge collects natural rainfall amounts that establish baseline water inputs for your garden ecosystem, allowing you to determine whether nature has provided adequate moisture or whether irrigation applications must supplement natural precipitation. This measurement eliminates guesswork about actual water inputs and prevents overwatering during periods when rainfall has already saturated soil conditions beyond optimal moisture tension ranges. The finger test performed at 6-inch depth throughout your garden provides significantly more relevant information than surface moisture readings that mislead irrigation decisions by reflecting only shallow soil conditions. Insert your finger directly into soil at multiple locations across your garden, pressing down until you reach the 6-inch depth where most plant roots actively absorb water and nutrients. The resistance encountered during insertion correlates directly with soil moisture tension levels that determine whether plants can extract available water through normal physiological processes. Soil that feels dry and crumbly at 6-inch depth indicates moisture tension levels have exceeded optimal ranges for most garden plants, signaling immediate irrigation needs before cellular stress damage occurs. Conversely, soil that feels saturated or muddy at depth suggests waterlogged conditions that create the oxygen starvation scenarios responsible for toxic metabolite production and root system destruction. Mulch depth measurements ensure consistent evaporation control throughout your garden while maintaining optimal moisture retention without creating suffocating conditions that eliminate soil oxygen availability. Measure mulch thickness across different garden areas to verify that organic material layers remain between 2 and 3 inches deep, providing effective evaporation barriers without blocking air exchange processes essential for root respiration. Insufficient mulch depth allows excessive water loss through surface evaporation, while excessive mulch thickness can create anaerobic conditions that promote harmful bacterial growth and root decay. Plant observation techniques reveal early water stress indicators, including subtle leaf color shifts, reduced morning turgidity, and decreased growth rates that signal developing moisture deficits before visible wilting damage occurs. Examine plant foliage during early morning hours when healthy. Well-hydrated plants display full leaf expansion and rigid tissue structure, indicating adequate cellular water pressure. Plants experiencing water stress demonstrate reduced leaf turgidity even during cool morning hours, revealing moisture deficits that require irrigation intervention before cellular damage progresses. Monitor leaf color changes that indicate developing water stress, including slight dulling of normal green pigmentation or subtle color shifts that occur before dramatic wilting symptoms become apparent. These early visual indicators allow proactive irrigation scheduling that prevents permanent cellular damage while maintaining optimal plant health throughout changing environmental conditions. Drip irrigation and soaker hose systems deliver water directly to root zones while eliminating leaf wetness that creates optimal conditions for fungal pathogen development and disease establishment. These targeted delivery systems apply water at soil level through controlled emission points that saturate root zones without wetting foliage surfaces, where disease organisms thrive during extended moisture exposure periods. The precise application eliminates water waste through evaporation and surface runoff while maintaining optimal soil moisture conditions without creating waterlogged environments. Install drip irrigation systems along plant rows or around individual specimens to ensure water reaches active root zones where absorption occurs most efficiently. Position soaker hoses beneath mulch layers to provide slow, steady water release that penetrates soil gradually without overwhelming plant water regulation systems or creating surface runoff that wastes applied moisture. Rain gauges provide baseline precipitation data, while finger tests reveal soil moisture tension throughout root zones where water extraction occurs. Mulch depth measurements ensure consistent evaporation control, while plant observations indicate developing stress before permanent damage occurs. Targeted irrigation systems deliver water efficiently while preventing disease-promoting leaf wetness that compromises plant health. The integration of these monitoring techniques creates comprehensive assessment protocols that respond to actual plant water requirements rather than predetermined schedules that ignore environmental variables and soil physics. Each tool provides specific information about different aspects of the garden moisture system, from rainfall inputs and soil conditions to plant responses and water delivery efficiency. These fundamental measurement approaches work together to reveal the invisible biological and physical processes that determine whether applied water supports plant health or triggers the destructive mechanisms that transform irrigation from life-giving care into systematic cellular destruction. The precision comes not from complex technology, but from understanding exactly what to measure, and when those measurements indicate optimal conditions for plant survival versus the deadly scenarios that most gardeners unknowingly create through improper timing and application methods. These measurement protocols transform complex irrigation management into systematic assessment techniques that respond to actual biological processes rather than arbitrary scheduling systems. The difference between thriving plants and root death lies not in water volume, but in understanding the invisible biological processes that determine when and how plants can actually utilize that water. Timing determines whether irrigation activates protective antioxidant systems or triggers fungal proliferation and toxic metabolite production within root tissues. Your garden operates as a dynamic system where soil moisture tension, plant circadian rhythms, and environmental conditions interact in ways that make rigid watering schedules obsolete. Professional agricultural operations demonstrate consistent success by monitoring these biological factors rather than following arbitrary volume measurements. Master these principles, and you'll transform destructive watering habits into precision irrigation that supports optimal plant health throughout changing environmental conditions.